In the early years of the 20th century, the universe was being rewritten by questions that no one fully understood. Light had been split. Electrons had been seen to dance in ways that defied reason, and the comfortable certainty of classical physics was beginning to tremble. Amid this scientific storm, there emerged a man whose imagination stretched beyond equations, a thinker who gazed into the invisible fabric of reality and saw waves where others saw chaos. His name was Erwin Schrödinger, and his journey into the unknown would transform not just physics, but the way humanity understood existence itself. Schrödinger was not a man content with the surface of things. He lived in a time when science was divided between the tangible and the mysterious, between Newton's predictability and Planck's new, uncomfortable quantization of energy. The atom was no longer a simple model, it was a world of shadows, flickering between what was known and what was guessed. Schrödinger stood at the edge of this uncertainty, watching the pieces of the universe drift like fragments of a dream, and he dared to ask, what if these fragments could be woven into something beautiful, something coherent, something that explained not only the behavior of particles, but the rhythm of existence itself? From his earliest years, Schrödinger was fascinated by patterns, the elegant, almost musical harmony that connected one idea to another. He believed that beneath the chaos of experimental data, there must exist a deeper order, something smooth and continuous, like waves upon a vast ocean of reality. The idea of the quantum world, filled with abrupt jumps and invisible boundaries, disturbed him. He found it inelegant, incomplete, and against the grain of nature's harmony. But rather than reject it, he chose to understand it on his own terms. His imagination became his laboratory. He began to picture particles not as solid points darting through space, but as waves of probability, spread out, overlapping, interacting with one another in ways that could be described by pure mathematics. It was a radical vision, one that broke away from the old mechanistic picture of the universe. In a world still clinging to Newton's clockwork cosmos, Schrödinger dared to imagine something entirely different, a universe made not of certainties, but of possibilities. The spark of his great idea came during a period of intense creativity and solitude. In 1925, Schrödinger retreated to a small cabin in the Swiss Alps, taking with him little more than notebooks, mathematical texts, and a restless mind. Outside, snow fell silently over the mountains. Inside, a new world was forming on the pages of his notes. It was here that he conceived the wave equation, a mathematical expression that would soon define the entire field of quantum mechanics. To him, it wasn't just an equation, it was a revelation, a vision of how the microscopic universe truly behaved. He imagined an electron not as a wandering particle, but as a wave that spread through space, resonating with energy and probability. The equation he wrote described how these waves evolved, how they interacted, and how they gave birth to the structures of matter. For the first time, the strange dual nature of particles, behaving both as matter and as waves, found a voice that made sense. The Schrödinger equation was not merely a scientific tool, it was a poetic bridge between the known and the unknown. Yet this visionary leap did not come easily. It defied the intuition of an age still grounded in the tangible. His contemporaries were skeptical. How could something that could not be seen, a wave of probability, be real? Schrödinger himself struggled with this paradox. He didn't just invent the mathematics, he wrestled with its meaning. What does it mean for a particle to exist as a wave? What happens when we observe it? Does the wave vanish, or does reality itself shift beneath our gaze? These were not just scientific puzzles, they were questions that touched the very core of philosophy, of being, of consciousness. Schrödinger's imagination reached where experiments could not. He saw the universe as something alive, dynamic, continuous, and deeply intertwined with the observer. He believed that nature was not random, but guided by underlying order, and his wave equation became the language through which that order could be expressed. It was an act of creation as much as discovery. For a moment, It seemed as though he had pulled the hidden music of the cosmos into the realm of human understanding. But Schrödinger's leap into the unknown was not simply a triumph of intellect, it was also a profound act of faith. He was stepping into a realm that could not yet be verified by experiment, guided only by intuition, reason, and a poetic sense of beauty. His ideas emerged from the conviction that nature's laws must possess elegance, that truth and beauty are two sides of the same coin, and in that faith he was vindicated. The wave equation worked. It predicted results with astonishing accuracy, describing atomic behavior with precision unmatched by any theory before it. Still, the world around him was changing fast. The quantum pioneers, Heisenberg, Born, and Dirac, were building their own interpretations of the subatomic world, each more abstract and unsettling than the last. Schrödinger's vision was different. It was gentle, continuous, and rooted in the belief that the universe was ultimately comprehensible. To him, the act of understanding nature was not about dissecting it into randomness, but about embracing its unity. And that unity, he believed, could be expressed through waves, the purest form of motion, energy, and existence. Schrödinger's leap into the unknown was not merely scientific. It was emotional, almost spiritual. It was a journey through doubt, wonder, and self-discovery. In his private writings, he often spoke of the world as a single organism, connected through invisible vibrations. He compared his discoveries to music, a symphony of invisible tones that only mathematics could hear. His wave equation became the score of that cosmic symphony, a melody that resonated through every atom, every photon, every pulse of existence. He was a man torn between logic and imagination, between the solid ground of science and the limitless skies of philosophy. But it was this tension, this inner duality, that made his vision so powerful. He could dream like a poet and reason like a physicist. He could look at an equation and see not symbols, but meaning, not numbers, but truth. When he gazed upon his own formula, he saw not just the mechanics of electrons, but the pulse of life itself encoded in mathematics. The world, however, was slow to catch up. When Schrödinger published his work in 1926, it was met with both admiration and confusion. Some physicists were ecstatic. They saw in his equation a key to unlock the mysteries of the atom. Others were hesitant, sensing that his theory opened doors to unsettling philosophical implications. The idea that reality existed only as a wave of probabilities, that observation itself could alter the nature of existence, was deeply disturbing. Schrödinger had not just rewritten physics, he had rewritten reality. His visionary leap was a bold act against the comfort of the known. It forced scientists to confront the limits of perception, to question what it means for something to be real. Was the universe a machine, predictable and solid, or was it a living wave of endless potential, collapsing into form only when observed? Schrödinger's work suggested the latter, a universe that was not fixed but fluid, shaped as much by consciousness as by matter. In many ways, Schrödinger's leap was also a reflection of his time, an age when humanity was standing on the threshold of modernity, caught between the certainties of the past and the infinite possibilities of the future. The world was rebuilding after war, technology was transforming lives, and the old ways of thinking were dissolving. In this atmosphere of change, Schrödinger's imagination became a beacon, illuminating the invisible architecture of the universe, and showing that even in chaos, there is order, even in uncertainty, there is beauty. He once said that the task of the scientist is not merely to collect facts, but to see the invisible connections that bind them together. This belief guided his entire career. To Schrödinger, science was not a mechanical process, but a human journey, a dialogue between mind and matter. His leap into the unknown was not blind, it was guided by intuition, by the conviction that truth lies beyond the surface of things. And when he looked into that abyss of uncertainty, he did not see darkness, he saw light, shimmering like waves upon the quantum sea. His discovery reshaped not just physics, but the philosophy of knowledge itself. Before Schrödinger, the world seemed composed of tiny, solid pieces. After him, it became a symphony of interactions, a web of vibrations that only appeared solid when observed. His imagination had transcended the limits of empirical observation and entered a domain where reality itself was flexible, alive, and deeply mysterious. To understand the magnitude of his leap, one must remember that he did this not with new instruments or machines, but with thought alone. His laboratory was his mind. His tools were mathematics, intuition, and imagination. He dared to think the unthinkable, to picture a universe that no one had ever seen. And in doing so, he changed the trajectory of science forever. Schrödinger's visionary leap into the unknown stands as one of the most profound moments in intellectual history, the moment when imagination proved itself as powerful as experiment, when the human mind touched the quantum fabric of reality and found it responsive. His work is a testament to the idea that truth often begins as a dream, fragile, uncertain, but luminous. Even as debates raged around him, Schrödinger remained calm, confident in the beauty of his creation. He once wrote that he was guided not by logic alone, but by an aesthetic sense, a belief that the laws of nature must be beautiful, simple, and harmonious. It was this faith in beauty that led him beyond the known, into the unseen, and it is this faith that still inspires scientists today. The years that followed the unveiling of Schrödinger's wave equation were years of wonder and debate. The scientific world stood on the edge of revelation, staring into a reality that refused to stay still. In lecture halls and late-night cafes, physicists argued over the meaning of this new picture of the universe. They debated not just the mathematics, but the philosophy buried within it, a philosophy that Schrödinger himself had only begun to grasp. For him, the equation was not just a tool for predicting results. It was a living symbol of something greater, a mirror reflecting the rhythm of existence itself. Schrödinger often spoke of the picture behind the math. To him, the wave function was not an abstraction. It was the very essence of being, a pulse that connected every point in space and time. Where others saw confusion, he saw unity. He imagined every atom as a tiny wave pattern within a vast cosmic sea, each vibration harmonizing with the next to create the grand composition of the universe. This vision was not cold or mechanical, it was alive, breathing, dynamic. It suggested that the universe was not made of separate objects but of interwoven patterns, all resonating in one infinite field of energy. But even as Schrödinger's ideas spread, they met resistance. The physicists of the new generation, Heisenberg, Bohr, and Born, were building their own interpretation, one that embraced uncertainty and dismissed the need for a physical picture. Bohr's Copenhagen interpretation declared that particles did not have definite properties until measured. Heisenberg's uncertainty principle added that one could never know both a particle's position and momentum at the same time. These ideas were bold, but they clashed with Schrödinger's deep belief in continuity and order. He resisted fiercely, not out of stubbornness, but out of conviction that the universe could not be reduced to randomness. He wrote to colleagues that he found it repugnant to think nature operated purely by chance. For Schrödinger, the wave was real, and its smooth evolution described something tangible, not just a shadow of probability. His leap into the unknown had been guided by faith in harmony, and he refused to let that vision dissolve into statistical fog. The debate became one of the most famous in scientific history, the struggle between the determinism of Schrödinger's waves and the indeterminacy of quantum mechanics. To illustrate the absurdity he saw in the Copenhagen view, Schrödinger imagined a now legendary thought experiment: a cat sealed inside a box, its fate linked to a quantum event. If quantum mechanics said a particle could be both decayed and not decayed, then the cat would be both alive and dead, until someone looked inside. It was not a literal experiment, it was a challenge, a philosophical weapon. Through this strange image, Schrödinger was asking the world, how can something exist in two contradictory states at once? Is reality waiting for our eyes to define it? Or does it exist independently, regardless of observation? That image, the cat caught between life and death, became immortal. It leapt beyond physics into art, literature, and culture, symbolizing the tension between knowledge and mystery. Yet beneath its irony lay Schrödinger's deeper pain, the fear that his vision of a continuous, meaningful universe was being replaced by a fragmented one, ruled by chance and observation. Still, even in disagreement, Schrödinger's influence was undeniable. His equation worked magnificently. It explained the structure of atoms, predicted the behavior of electrons, and gave scientists a framework that has survived a century of tests. Every time a quantum computer processes information, every time a laser beam cuts through glass or a semiconductor chip powers a device, Schrödinger's waves whisper in the background. His imagination, once considered too abstract, became the blueprint for the modern technological world. In quiet moments, Schrödinger reflected on how far his leap had taken him. He had turned mathematics into a language capable of describing the invisible. He had built a bridge between the physical and the philosophical, and yet he sensed that the journey was incomplete. There was still something missing. A connection between the quantum world and consciousness itself. For Schrödinger, it was unthinkable that mind and matter could be separate. He believed they were two expressions of the same underlying reality. He once wrote, "The total number of minds in the universe is one." It was a statement not of mysticism, but of unity, the same unity that his wave equation had revealed on the microscopic scale. As he aged, Schrödinger's work drifted more deeply into the philosophical. He turned his attention to the question of life itself, how living systems emerge from the dance of atoms. His book What is Life, published in 1944, planted the seeds for an entirely new science. In it, he proposed that the secret of heredity lay in molecular structures that stored information in orderly patterns. Those words would later inspire Watson and Crick to search for the structure of DNA. In a way, Schrödinger's imagination once again reached across disciplines, showing that the same principles guiding electrons could also describe the code of life. His leap into the unknown had not been limited to the quantum world, it had expanded into the biological, the philosophical, even the spiritual. He saw existence as a continuum, from the smallest wave to the consciousness that perceives it. His was a vision of interconnectedness, where every thought, every atom, every beam of light was part of a single, undivided reality. This was not the mechanistic universe of classical physics. It was a living universe, aware of itself through the eyes of its observers. There is something profoundly human in Schrödinger's journey. He was not a detached mathematician hidden behind formulas, he was a seeker of meaning. His equations were expressions of wonder, his theories acts of imagination. He stood at the intersection of science and poetry, of reason and intuition, and refused to choose one over the other. His leap into the unknown was not only about discovering how electrons move, it was about discovering how we understand the universe and ourselves. Imagine a man sitting by a window as twilight fades, his desk lit by the soft glow of a lamp. Outside, the world moves in silence. Inside, his pen moves across paper, tracing symbols that describe the behavior of everything that has ever existed. Those lines are more than mathematics, they are music, a song of waves, a symphony of being. In that quiet room, Erwin Schrödinger was not simply writing equations, he was listening to the heartbeat of the cosmos. He had found a way to let imagination speak in the language of physics. Today, nearly a century later, the legacy of that imagination endures. Quantum mechanics remains both the most accurate and the most mysterious theory ever devised, and at its heart still lies the wave, the concept that Schrödinger brought to life. Every experiment that confirms quantum behavior, every discovery that challenges our understanding of reality, echoes his vision. Even the paradoxes he struggled with, superposition, entanglement, the role of the observer, have become the frontier of modern science. The quest for quantum reality continues to follow the trail he began. Physicists now speak of quantum fields, strings, and multiverses, ideas that stretch imagination to its limits. Yet beneath all these theories, the essence of Schrödinger's leap remains unchanged: the belief that reality is deeper, stranger, and more unified than we can see. His wave equation was more than a description. It was a philosophy, an invitation to think differently. It reminds us that knowledge grows not from certainty, but from wonder, from daring to imagine beyond what we know. Schrödinger's leap into the unknown is not confined to the pages of physics textbooks. It lives in every scientist who dares to dream. It lives in the researcher who looks at an equation and senses beauty. It lives in the philosopher who wonders if observation shapes existence. It lives in the engineer who designs a quantum circuit, unaware that its mathematical heart beats with Schrödinger's rhythm. It even lives in the poet who sees in the night sky not emptiness, but infinite possibility. His vision has transcended its origin, becoming part of the collective imagination of humankind. In retrospect, what makes Schrödinger's leap so extraordinary is not that he solved a problem, but that he expanded the definition of what it means to understand. Before him, physics sought to describe the world as it is. After him, physics began to describe the world as it could be, a fluid reality shaped by observation, probability, and connection. His imagination opened doors that science is still walking through, revealing a universe that is less a machine and more a mystery. Not static, but alive. As we stand today, on the brink of a new quantum revolution, Schrödinger's presence can still be felt. Quantum computers are being built that manipulate waves of probability directly. Quantum cryptography promises unbreakable security by harnessing the same principles that once existed only in his mind. In laboratories across the globe, researchers chase the dream of understanding consciousness, exploring whether the observer's role in quantum theory hints at something deeper about awareness itself. Everywhere, the echoes of Schrödinger's vision resound, the dream of turning imagination into reality. And so, the story comes full circle. The man who once sat in solitude among the Alps, sketching equations that seemed like fantasies, has reshaped the modern world. The imagination that led him into the unknown has become the foundation of technology, philosophy, and human thought. His leap reminds us that discovery is not the opposite of dreaming. It is the fulfillment of it. Every great leap in science begins not with evidence, but with a question that refuses to fade. If one listens closely, perhaps one can still hear the waves he described, the silent oscillations of matter and mind, rippling through the fabric of the universe. They remind us that imagination is not separate from reality, it creates it. Schrödinger's journey was never about escaping the unknown, but embracing it, walking into it with courage, curiosity, and wonder. In that sense, Erwin Schrödinger was more than a physicist. He was an explorer of existence, a poet of mathematics, a philosopher of waves. His leap into the unknown was not a single act, but a legacy, one that continues to inspire every attempt to see beyond the visible, to reach beyond the measurable, and to understand that the boundaries of the universe are only the boundaries of our imagination. And so the story of Schrödinger's visionary leap is not finished. It continues wherever curiosity lives, in classrooms, in observatories, in quiet minds asking impossible questions. His wave still moves through time, invisible but eternal, whispering to all who listen that the unknown is not to be feared, but embraced, because beyond the known lies the realm of imagination, and it is there, in that infinite sea, that reality itself begins. In the quiet dawn of the 20th century, physics was standing at a crossroads. The once solid foundation of classical science was trembling under the weight of discoveries that refused to obey its laws. Light behaved as both particle and wave. Matter, once thought to be stable and indivisible, was found to exist in mysterious, flickering states. The atom, long imagined as a miniature solar system, no longer fit the equations that had once seemed eternal. The great minds of the age, Planck, Einstein, Bohr, had cracked open a door to the quantum world, but beyond that door lay chaos, paradox, and silence. And then, out of that silence, came a voice, calm, curious, and imaginative. It was the voice of Erwin Schrödinger, the man who would turn confusion into music and birth an equation that would redefine what it means to understand the universe. Schrödinger was not a man of explosions or bold proclamations. His genius worked in quiet revolutions, in the stillness of deep thought. The story of the wave equation did not begin in a laboratory or a grand observatory. It began in solitude, in a room filled with notes, chalk, and restless imagination. To understand how his equation was born is to journey into the mind of a thinker who sought harmony in a universe that seemed fractured. In the early 1920s, quantum theory was a patchwork of strange rules. Max Planck had discovered that energy came in discrete packets, or quanta. Einstein had shown that light could behave like particles, and Niels Bohr had built a model of the atom that worked, but only through mathematical guesswork and abrupt assumptions. There was no underlying theory to explain why it worked. The equations of classical mechanics, which had once described planets and pendulums, failed when applied to the world of electrons. Physics had entered a wilderness of uncertainty, and Schrödinger could feel it pressing on his mind. He was driven by something deeper than curiosity, by a longing for beauty, for continuity, for the sense that nature's laws must sing with elegance. The broken patterns of early quantum theory seemed wrong to him, not because they failed experimentally, but because they lacked grace. He believed the universe was fundamentally wave-like, smooth, continuous, and mathematical. And so, while others accepted the disjointed quantum rules, Schrödinger began searching for the deeper melody beneath the noise. In the winter of 1925, he withdrew from the world. He retreated to the Swiss Alps, escaping not only the noise of cities but the confusion of physics itself. There, surrounded by snow and silence, he began to think. In the stillness of those mountain days, he imagined particles not as tiny balls of matter, but as waves moving through a vast field of possibilities. The concept had been hinted at before. Louis de Broglie had suggested that matter might possess wave-like properties, but no one had yet found a way to describe it precisely. Schrödinger wanted to give that idea form. He wanted an equation that could speak the language of nature's most intimate processes. For weeks, he filled his notebooks with equations and sketches. He studied de Broglie's ideas, the mathematical forms of energy and motion, and the relationships between frequency, wavelength, and momentum. He began to see a pattern forming, a bridge between the physical and the mathematical. The waves he envisioned were not like waves of water or sound. They were waves of probability, invisible patterns that determined where a particle might be found, how it might move, and how it interacted with the universe around it. Each night he tested new forms of equations, shaping and reshaping them with the precision of a sculptor. And then, as if nature herself whispered the answer, he found it, a simple, elegant expression that described how these quantum waves evolved in time and space. It was unlike anything physics had seen before. It did not describe the path of a particle, but the state of a system. A complete description of everything that could be known about it. The equation was breathtakingly beautiful, compact yet infinite in meaning. It could describe the motion of electrons within atoms, the behavior of energy in light, even the structure of molecules. It was the missing link, the key that transformed chaos into coherence. Schrödinger's wave equation was not just a formula, it was a revelation, a new way of thinking about existence itself. In its simplest form, the equation was a bridge between energy and motion, between possibility and reality. It said that every particle could be represented by a wave function, a mathematical object that held all the information about the particle's behavior. The square of this function revealed the probability of finding the particle at a particular point in space and time. It was as if Schrödinger had written down the invisible architecture of the cosmos, the rules by which reality oscillates between what is possible and what is real. When Schrödinger first shared his results, the scientific world was astonished. For years, physicists had been struggling to understand how the quantum world could be described. His equation not only explained it, but did so with a kind of poetry. In a few lines of mathematics, he had unified the broken fragments of theory into a single, harmonious vision. The wave equation was soon tested against experimental results, and it worked with extraordinary precision. It explained the structure of hydrogen atoms, predicted energy levels, and revealed patterns that matched perfectly with what scientists had observed in the laboratory. It was as if the universe itself had been waiting for someone to write this equation, as if the waves that underlay reality had been singing all along, and Schrödinger had finally learned to hear them. The birth of the wave equation was a moment of scientific creation as profound as any in history. It was the moment when the invisible became visible through the power of imagination and mathematics. But what truly set Schrödinger's work apart was not just its accuracy, it was its vision. He had not derived his equation from experiment, he had dreamed it into being. His imagination, guided by intuition and aesthetics, had reached beyond data to reveal a truth that no one had yet seen. He once remarked that his goal was not to find a mathematical trick, but to understand the meaning of the quantum world. The equation for him was a window into the soul of nature. In those days, the debate over quantum theory was fierce. Werner Heisenberg had just proposed a radically different approach based on matrices rather than waves. His version worked too. It produced the same results, but it offered no clear picture of what was happening beneath the surface. It was abstract, mechanical, and devoid of imagery. Schrödinger's equation, on the other hand, painted a vivid picture. It suggested that the universe was filled with smooth, flowing waves, each representing the potential of existence. Where Heisenberg saw uncertainty, Schrödinger saw harmony. Where others saw probability, he saw pattern. When Schrödinger presented his work in 1926, it was more than a mathematical paper, it was a statement of philosophy. He was declaring that reality was not fragmented or chaotic, but continuous and interconnected. The wave equation became his proof, a testament to the unity of the cosmos. The world of the very small, he argued, was not governed by sudden jumps or random events, but by waves that moved and interacted with grace and order. His equation, written in symbols, was deceptively simple, yet its implications were endless. It described the energy of a system in terms of its wave function, a function that evolves smoothly over time. This evolution, governed by Schrödinger's equation, became the foundation of quantum mechanics. It allowed scientists to calculate how atoms bond, how light interacts with matter, and how the smallest particles give rise to the grand structures of the universe. From the glow of stars to the circuits of modern computers, the ripples of that equation reach everywhere. And yet, Schrödinger himself was never entirely satisfied. The equation he had birthed worked with stunning accuracy, but its meaning remained elusive. What was the wave function, really? Was it a physical wave, something that existed in the world, or merely a mathematical tool for predicting probabilities? Schrödinger longed for it to be real, to represent something tangible, something that flowed through space like an invisible ocean. But as other physicists embraced the probabilistic interpretation, his vision was challenged. They said the wave was not real, that it was only a description of knowledge, not of existence. To Schrödinger, that was like saying music was not real because one could not touch it. Still, his creation endured. The wave equation became the heart of quantum mechanics, the tool through which generations of scientists explored the unseen. It explained chemical reactions, nuclear processes, and even the behavior of matter under extreme conditions. It led to the birth of quantum chemistry, solid-state physics, and the technologies that power the modern world. Every time a transistor switches, every time a laser emits light, every time an electron moves through a circuit, Schrödinger's waves are at work. Silent, precise, eternal. To witness the birth of the wave equation is to witness the moment when human thought reached beyond the senses and touched the fundamental rhythm of reality. Schrödinger's insight showed that the universe is not made of things, but of patterns, patterns that pulse, interfere, and evolve like waves on an infinite sea. His equation became the compass by which humanity could navigate that sea, revealing not only where particles are, but how they become. And so, what began as a search for beauty in mathematics became a revelation about the nature of existence. Schrödinger's wave equation was not only a triumph of intellect, but of imagination. It was proof that the universe, in all its mystery, can be written in symbols, that the language of waves is the language of reality itself. As he stood before his peers, unveiling his creation, Schrödinger must have sensed that he had crossed a threshold. Behind him lay the world of certainty, of particles and orbits. Ahead lay the world of probability and possibility, a world that could no longer be seen with the eyes, but only with the mind. His equation was a doorway into that world, and once opened, it could never be closed again. In the later years of his exploration, Schrödinger began to realize that the wave equation was not merely an isolated triumph of mathematics. It was a portal into the hidden structure of existence itself. Every symbol within that equation carried a pulse of meaning, a whisper of how the universe truly behaved beneath the surface of certainty. His mind, forever restless, began to search for what lay beyond the formula. The equation, he thought, was not the end of inquiry, but the beginning of an even deeper mystery. The mystery of interpretation. What does it mean for a wave to describe a particle? What does it mean for existence to be governed by probability? These were not just questions of physics, but of philosophy, of reality itself. As Schrödinger continued his journey, he found himself both celebrated and misunderstood. To many, his wave equation was a triumph of pure genius. To others, it was a challenge to intuition, an invitation to embrace a world that could not be seen or touched, but only imagined through numbers. Yet Schrödinger's strength was precisely this. He could bridge the gap between imagination and logic, between the abstract and the tangible. In his mind, the universe was a grand symphony, and the wave equation was its sheet music. Each particle played its part, guided not by rigid rules, but by probabilities that danced through invisible waves. The world around him, however, was still catching up. The quantum realm defied the comfort of classical physics, which had given humanity centuries of certainty. The Newtonian world was one of predictability. Cause and effect, motion and response, a universe that behaved like a finely tuned machine. But Schrödinger's vision dismantled that mechanical comfort. He revealed a cosmos that was alive with possibilities, where outcomes could not be predicted with absolute precision, where observation itself changed the very state of what was being observed. It was a revelation both thrilling and terrifying, a scientific awakening that demanded humanity to rethink its place in the grand order of things. In this new landscape, Schrödinger's wave equation became a lighthouse, guiding physicists through the fog of uncertainty. It described not the position of a particle, but the likelihood of its presence. This idea alone reshaped the entire meaning of reality. It suggested that at its deepest level, existence was not fixed but fluid, a sea of potentialities waiting to collapse into form. The equation was both a description and a prophecy, a promise that nature could be understood, even if only in terms of probabilities. Schrödinger's vision was revolutionary because it accepted the mystery without fearing it. He saw beauty in uncertainty, structure in chaos, and meaning in abstraction. But what truly made Schrödinger's contribution timeless was his human touch. He was not a detached mathematician hidden behind his formulas. He was a philosopher of being, a dreamer who saw in quantum theory the echoes of life itself. He often reflected on how the behavior of particles resembled the rhythms of consciousness. Unpredictable yet patterned, mysterious yet interconnected. For him, the universe was not a machine of matter, but a living field of awareness. His wave equation was not just a physical law, it was a mirror reflecting the unity between observer and observed. In this unity, Schrödinger found something profoundly spiritual, a sense that the laws of physics were not cold or indifferent, but alive with creative potential. The scientific community, however, remained divided. Some, like Heisenberg and Bohr, celebrated the probabilistic nature of the quantum world. Others longed for something more deterministic. Schrödinger himself wrestled with this duality. He admired the mathematical precision of his equation, but questioned what it truly meant for something to exist. Was the wave real, or merely a mathematical convenience? Did particles exist in some strange superposition of possibilities until observed, or was that just a human interpretation of a deeper truth? These questions gave birth to debates that continue to this day. Debates about measurement, observation, and the very nature of reality. Despite his own doubts, Schrödinger's wave equation endured because it worked. It predicted results that could be tested, measured, and proven. From the structure of atoms to the behavior of electrons, his formula became a cornerstone of quantum mechanics. The accuracy of its predictions was unmatched, and it opened the door to discoveries that would transform modern technology. Lasers, transistors, semiconductors, all trace their roots back to the understanding Schrödinger helped create. The once invisible waves he described now power the very heart of human civilization. His imagination had quite literally become reality. And yet, beyond the achievements and accolades, Schrödinger remained deeply reflective. He wondered if humanity was ready to accept the philosophical consequences of his work. If the universe was truly built on probabilities, if certainty was an illusion, what did that mean for human understanding? Were we merely observers of an unfolding cosmic dance, or were we participants shaping it with our awareness? These thoughts lingered in Schrödinger's writings and letters, revealing a man who was both scientist and seeker. His pursuit of knowledge was inseparable from his search for meaning. As years passed, the wave equation continued to evolve in the hands of new generations of physicists. They refined it, expanded it, and applied it to realms Schrödinger could never have imagined. Quantum computing, information theory, the study of black holes. Each new discovery added another layer to his legacy, and through it all, his equation remained a symbol of the power of the human mind to reach beyond what is known. It was proof that imagination, guided by intellect, could pierce the veil of the invisible and reveal the architecture of the cosmos. In the twilight of his life, Schrödinger often looked back on the path he had walked. He had ventured into the unknown with nothing but thought and intuition as his guide. What he discovered there changed not only science but the very way humanity understood existence. The wave equation had begun as a mathematical dream, but it became a map of reality, a map drawn not in ink, but in imagination. And as the world continues to explore the quantum frontier, Schrödinger's voice still echoes through the corridors of physics, reminding us that every great discovery begins with a question, every equation begins with wonder, and every leap into the unknown begins with the courage to imagine what has never been seen before. Erwin Schrödinger's journey from curiosity to creation was not just the story of one man, it was the story of human progress itself. He showed that science is not confined to laboratories or blackboards. It lives in the human spirit's relentless desire to know, to question, to dream. Through his wave equation, he gave humanity a new way to see the universe, one that replaced certainty with curiosity and rigidity with freedom. His legacy stands as an eternal invitation to every thinker, every dreamer, every scientist to step beyond the known, to follow the whisper of intuition, and to remember that the greatest discoveries often begin in the quiet realm of imagination. Under the pale glow of the early 20th century, the world of science stood on firm ground. Physics was a triumph of certainty, a proud monument built on the laws of Newton and Maxwell, where every motion could be predicted, every outcome measured, every cause followed by its effect. The universe was a grand machine, a perfect mechanism wound by the hand of logic. Nature, it seemed, was completely understood. But in that age of confidence, a quiet storm was brewing, a storm that would unravel the very fabric of this classical certainty. And at the heart of that storm stood Erwin Schrödinger, a man who dared to question whether reality itself could be trusted. For centuries, classical physics had offered comfort in its clarity. Objects existed in definite places, events followed predictable paths. To the human mind, this view of reality made sense. It mirrored our everyday experience. Yet, in the hidden world of atoms, something strange was happening. Experiments showed that particles behaved in ways that defied all logic. They could pass through two slits at once, exist in multiple states, or vanish into waves of probability before reappearing as solid matter. It was a world where the familiar rules no longer applied, and Schrödinger found himself standing before this abyss, peering into the unknown. The classical physicist within him resisted. He had grown up in a world where order ruled, where equations described predictable motion. But as he immersed himself in the discoveries of Planck, Einstein, and Bohr, Schrödinger began to feel the tremors of something far greater. There was a beauty hidden in this uncertainty, a deeper truth waiting to be unveiled. He realized that the rigid walls of classical thought could no longer contain the mysteries of the quantum world. To truly understand reality, he would have to challenge everything he had once believed. Schrödinger's challenge began not with rebellion, but with curiosity. He did not seek to destroy classical physics, but to expand it, to find a bridge between the tangible and the invisible. The classical world described how things moved. Schrödinger wanted to understand what things were. When he studied the electron, he saw not a tiny billiard ball orbiting a nucleus, but something more abstract, a field of possibilities, a vibration, a wave that existed not in space alone, but in a realm of potential. The mathematics that guided him was unfamiliar and strange, yet it whispered to him of a new reality, one where existence was not fixed, but fluid. As he developed his wave equation, Schrödinger found himself standing at the boundary between two worlds, the familiar order of classical mechanics and the uncharted territory of the quantum. The old laws could no longer explain the behavior of atoms. Something deeper, more mysterious, was shaping the microcosm. Schrödinger's equation gave that mystery a language, a way to describe the invisible currents of the universe. But in doing so, it also tore apart the comfortable assumptions of centuries. It declared that reality, at its core, was not made of solid objects moving through space, but of waves of probability, shimmering patterns that only became real when observed. This idea was nothing short of revolutionary. It meant that the universe was not a machine, but a symphony of possibilities. It meant that what we call reality was not a fixed stage, but a performance that changed the moment it was seen. For Schrödinger, this realization was both thrilling and unsettling. He admired the beauty of his equation, but struggled to accept what it implied, that certainty might be an illusion, and that observation itself could shape existence. In challenging the boundaries of classical reality, Schrödinger found himself questioning not only the nature of matter, but the nature of truth. He began to see that classical physics had been a reflection of human comfort, a mirror of our desire for stability in a world that feels unpredictable. But nature, he realized, was not beholden to human expectations. It followed its own rhythm, one that could not be confined by the logic of cause and effect. The wave equation did not describe a universe of fixed states, but one of superpositions, of multiple realities existing side by side until the act of observation brought one into being. The implications of this were enormous. It suggested that reality was participatory, that the observer and the observed were entangled in a cosmic dance, each defining the other. This revelation shook the foundations of scientific thought. For the first time, physics was not just about matter and motion, it was about consciousness, perspective, and perception. Schrödinger had crossed a line that many of his contemporaries were afraid to approach. The classical world was built on objectivity, on the idea that the universe existed independently of who observed it. But in the quantum realm, that independence dissolved. Reality was no longer a stage set apart from the observer. It was a creation in which the observer played a vital role. This idea defied centuries of philosophy and redefined the relationship between mind and matter. Schrödinger's journey into this strange territory was not without struggle. He admired the mathematical precision of his equation, but wrestled with its philosophical consequences. Could he, a scientist trained in logic and reason, truly accept a universe that behaved in such irrational ways? He found himself caught between the clarity of mathematics and the ambiguity of meaning. The classical physicist within him yearned for simplicity, but the quantum explorer in him saw beauty in complexity, and so he continued to walk the line between worlds, neither abandoning classical physics nor fully surrendering to quantum mystery, but embracing the tension between them as the source of progress. As he refined his theory, Schrödinger's ideas began to ripple through the scientific community. Some embraced them with awe, others met them with skepticism. The older generation of physicists found it difficult to let go of the tangible world they had built their careers upon. But the younger thinkers, inspired by the wave equation's elegance, began to see the universe in a new light. They realized that to understand reality, one must first accept its duality, its ability to be both particle and wave, definite and uncertain, real and potential. Schrödinger's challenge had not just rewritten physics, it had redefined the very meaning of existence. Yet, amid this revolution, Schrödinger remained humble. He did not see himself as the destroyer of classical thought, but as its evolution. He respected Newton's clarity and Maxwell's precision, but he believed that science must evolve just as the universe itself evolves, endlessly unfolding, endlessly surprising. He often reflected that the greatest danger in science was complacency, the belief that everything essential had already been discovered. To challenge classical reality was to keep curiosity alive, to keep asking the questions that others feared to ask. In his private moments, Schrödinger saw the beauty of his discovery not only in scientific terms but in philosophical ones. He believed that the universe was not divided into parts but woven together as a single tapestry of existence. Classical physics had separated things, matter from energy, observer from observed, cause from effect, but the quantum world revealed their unity. To him, this unity was not just a physical truth, but a spiritual one. It hinted at something profound, that all things, from the smallest particle to the vastness of the cosmos, were connected through the same invisible wave of being. This vision, born of mathematics and imagination, reshaped humanity's understanding of reality. It taught scientists to embrace uncertainty, to see beauty in paradox, and to accept that truth could exist in probabilities rather than absolutes. Schrödinger's challenge was not a rejection of the old, but a renewal of wonder. He showed that the universe is not a closed system of facts, but an open field of discovery, where each question leads to another, and each observation creates new possibilities. By daring to question the classical world, Schrödinger did more than change physics, he changed the way we see ourselves. He revealed that knowledge is not about mastering reality, but participating in it. That the universe is not something separate from us, but something we help to define. His journey was a testament to the power of imagination, the courage of doubt, and the endless pursuit of truth. And as the quantum world continues to expand before us, his voice still echoes through the fabric of science, whispering a timeless reminder that every boundary we challenge brings us closer to understanding the infinite mystery of existence itself. As the echoes of his revolutionary equation spread through the scientific world, Schrödinger found himself both celebrated and conflicted. He had unveiled a truth that stood at odds with centuries of certainty, a truth that dared to suggest the world was not what it seemed. To the classical mind, reality was something fixed, a stone, a star, a motion through space. To Schrödinger, reality had become something fluid, a shimmering field of potential that existed only in the act of becoming. It was an idea so profound that even he, its creator, struggled to accept it fully. The boundaries between imagination and reality, between the known and the unknowable, were dissolving before his eyes. Schrödinger's challenge to classical thought was not born from defiance but from necessity. The evidence had become undeniable. Light and matter behaved both as waves and as particles. The old frameworks of Newtonian physics could no longer explain the mysteries unfolding in laboratories around the world. Schrödinger's wave mechanics stepped into that void, not to destroy what came before, but to complete it, to show that the universe was more complex, more dynamic, and more alive than anyone had imagined. Yet, as this new theory took root, the comfort of classical determinism began to crumble. The notion that one could predict the future with perfect accuracy was replaced by a universe of probabilities, where even the smallest act of measurement could alter the outcome. This realization created a new tension in science, a philosophical battle between two ways of seeing the world. On one side stood the champions of classical clarity, clinging to the idea of an objective universe that existed independently of observation. On the other stood the pioneers of quantum uncertainty, embracing a reality woven from chance and observation. Schrödinger stood at the center of this storm, a bridge between the two realms. He respected the old laws, yet he could not ignore the truths the quantum world revealed. The equations spoke clearly: matter was not solid, it was wave-like, its position uncertain until seen. But what did that mean? What kind of world was this, where being depended on observation, where existence was fluid until fixed by consciousness? The questions haunted him. For Schrödinger, the mathematics was undeniable, but the implications were unsettling. If observation determined reality, then where did the observer fit in? Was consciousness itself a part of the universe's machinery, or was it something greater? A participant in creation? These were not the questions of a typical physicist, but Schrödinger was no ordinary scientist. He was a philosopher of nature, one who saw beyond numbers into meaning. His work became not just a scientific theory, but a meditation on existence. He began to realize that the classical world had been an illusion of simplicity. The universe, beneath its visible order, was a realm of constant transformation, of waves colliding, interfering, and blending in endless motion. The boundaries we perceive, between matter and energy, between observer and observed, are not fixed but fluid. In this understanding, the old walls of classical thought collapsed, revealing a deeper unity. Schrödinger's challenge was not just to physics, but to perception itself. He showed that the universe is not something out there, separate from us, but something we are intimately entangled with. The famous cat, alive and dead at once, became the perfect symbol of this new reality. In that imagined box, Schrödinger captured the absurdity of a universe that defied logic. He never meant the cat to be taken literally. It was a protest, a poetic mirror held up to quantum theory. He wanted the world to see the paradox, to confront the uneasy truth that the act of observation defines what is real. In that paradox lay the collapse of classical thinking and the birth of a new way of seeing. This idea reshaped the foundations of modern science. Suddenly, physics was no longer a quest for absolute certainty, but a dance with probability. It became a study not of what is, but of what could be. Schrödinger's wave mechanics gave scientists the power to predict the behavior of the atomic world, but it also reminded them of the limits of human understanding. His work taught the world that knowledge is not about controlling nature, but about learning to coexist with its mystery. Beyond the walls of academia, his ideas seeped into philosophy, art, and even spirituality. Thinkers began to see parallels between the quantum world and ancient wisdom, between the idea of unity in physics and the interconnectedness of all life. Schrödinger himself drew from such traditions, seeing in them reflections of his own discoveries. To him, the universe was not mechanical but conscious in some profound sense, a vast field of awareness expressing itself through form and energy. In this view, reality was not static but emergent, not separate but whole. Yet, despite this grand vision, Schrödinger remained grounded in humility. He often admitted that his wave equation, elegant as it was, revealed only a shadow of the full truth. The deeper meaning of reality, he believed, lay beyond human reach, in the mystery itself. But he also believed that to approach that mystery was the very purpose of science. Classical physics had sought to define, quantum physics sought to understand. It was a shift from mastery to wonder, from domination to participation. The challenge to classical reality was therefore more than a scientific revolution, it was a spiritual awakening. It forced humanity to confront its place in the cosmos. We were no longer mere observers of an external world, we were part of its unfolding. Every measurement, every observation, every act of awareness was a thread in the fabric of existence. Schrödinger's work became a mirror reflecting this truth that consciousness and the universe are not separate, but two sides of the same wave. Over time, his challenge inspired new generations of thinkers. Quantum mechanics evolved, expanding into new territories: quantum field theory, quantum computing, quantum biology. Each of these fields carried Schrödinger's imprint, each a continuation of his daring question, what is real? Even as the mathematics grew more complex, the philosophical heartbeat remained the same. Reality is not fixed, it is dynamic. It is not absolute, it is participatory. It is not merely observed, it is co-created. In the laboratories of the 21st century, scientists now manipulate quantum states that exist in multiple configurations at once, superpositions that defy classical description. They teleport information across distances, entangle particles that share the same state, no matter how far apart they are. Every one of these achievements is a living echo of Schrödinger's challenge, a testament to his vision. He turned science from the study of what was into the exploration of what could be. His legacy is not confined to textbooks, it is alive in every quantum experiment, every leap into the invisible. Looking back, one can see that Schrödinger's challenge was not an act of destruction, but of creation. He dismantled the comfort of certainty to reveal the beauty of mystery. He showed that the boundaries of classical reality were not limits, but gateways, doorways to a universe more magnificent than the human mind can fully grasp. In doing so, he reminded the world that science is not a fortress of facts, but an ocean of questions, and that the true power of the human spirit lies not in what it knows, but in what it dares to imagine. As the world continues to explore the quantum frontier, Schrödinger's words still resonate, a soft, eternal echo across time. He showed that imagination and reason are not opposites but allies, that to understand the universe, one must be willing to dream beyond its edges. The boundaries of classical reality were never walls, they were horizons. And beyond those horizons lies the infinite field of possibility, the very essence of quantum reality that Schrödinger helped humanity to see. In the annals of scientific thought, few images have captured the imagination of the world quite like the cat in the box. Schrödinger's cat is more than a whimsical experiment, it is a profound symbol, a mirror held up to the perplexing and paradoxical nature of quantum reality. It embodies the tension between what we think we know and what actually exists, between certainty and possibility, between observation and reality itself. When Erwin Schrödinger devised this thought experiment, he was not trying to frighten or confuse, he was challenging the world to confront the contradictions at the heart of quantum mechanics. The premise is deceptively simple. Imagine a cat enclosed in a sealed box, along with a mechanism triggered by the decay of a single radioactive atom. If the atom decays, a poison is released and the cat dies. If it does not decay, the cat lives. According to the principles of quantum mechanics, the atom exists in a state of superposition, both decayed and not decayed, until it is observed. In this strange framework, the cat, linked to the atom, also exists in a superposition, simultaneously alive and dead, a living paradox. Only when the box is opened, when an observer finally looks, does the cat resolve into one reality. This idea was more than a clever mental image, it was a direct confrontation with the limitations of classical reasoning. In the everyday world, objects have definite states. A cat is alive or dead, a ball is here or there. But the quantum world does not conform to such simplicity. Schrödinger's cat dramatizes this conflict, showing us that the microcosmic rules of nature defy our intuition, and challenge our understanding of existence. By connecting the fate of a familiar, living creature to the uncertain state of an invisible atom, he forced the human mind to grapple with the implications of a reality that cannot be fully observed or predicted. The thought experiment also highlights the active role of the observer. In classical physics, measurement is passive. We observe, and reality continues unchanged. In quantum mechanics, observation itself plays a crucial role. The act of measuring collapses probabilities into a single outcome. Until observation occurs, multiple possibilities coexist, intertwined in a delicate, ephemeral balance. Schrödinger's cat made this abstract principle tangible, illustrating that reality, at its most fundamental level, is participatory. It is not merely out there, waiting to be discovered, but shaped by the very act of perception. Beyond its scientific meaning, the cat resonates on a philosophical level. It forces us to question the nature of reality and our place within it. Can something exist in contradictory states? Does the universe require consciousness to define its outcomes? Schrödinger himself used the image as a critique of the Copenhagen interpretation of quantum mechanics, which suggested that particles exist only as probabilities until observed. He found this notion unsettling, even repugnant, because it seemed to place the entire universe under the control of human observation. The cat, simultaneously alive and dead, symbolizes this tension, a reality caught between objective existence and subjective perception. Culturally, the cat has become a symbol far beyond physics. It appears in literature, art, and popular imagination as a metaphor for uncertainty, ambiguity, and duality. It challenges our desire for clarity, forcing us to accept that not all questions have immediate answers, that some truths exist in flux. Its paradoxical nature mirrors the broader human experience, the tension between expectation and reality, between what is known and what is possible. In this sense, Schrödinger's cat is both a scientific tool and a mirror for philosophical reflection, bridging the worlds of physics and human thought. The enduring power of this thought experiment lies in its ability to simplify the complex without diminishing its depth. While quantum mechanics can be mathematically dense and conceptually counterintuitive, the cat brings it into the realm of imagination. By situating a familiar, living creature within the enigmatic rules of the quantum world, Schrödinger created a tangible way to explore abstract ideas. The cat forces us to visualize the invisible, to feel the tension of superposition, and to confront the paradoxes that lie at the foundation of modern physics. It is also a reminder of the limits of our knowledge. In a universe governed by probabilities and possibilities, certainty is a luxury we cannot always afford. The cat exemplifies the strange beauty of a world where potential and reality coexist, where outcomes are not fixed until interaction occurs. Schrödinger's imagination turned the abstract mathematics of wave functions into a story that resonates across disciplines, highlighting the interplay between science, philosophy, and perception. Ultimately, the mysterious cat is a celebration of curiosity and critical thought. It encourages questioning, challenges assumptions, and inspires exploration of the unseen. Schrödinger's genius lay not only in his mathematical insights, but in his ability to craft vivid, enduring images that communicate the essence of quantum mystery. The cat remains a timeless reminder that reality is more complex than appearances, that observation and understanding are deeply intertwined, and that the universe, in all its strangeness, invites us to participate in its unfolding drama. Even a century later, Schrödinger's cat continues to provoke thought, inspire debate, and symbolize the delicate balance between knowledge and mystery. It is at once a scientific tool, a philosophical emblem, and a cultural icon, a testament to the power of imagination to illuminate the hidden layers of reality. Through this paradoxical feline, Schrödinger challenged the world to see beyond the obvious, to embrace uncertainty, and to accept that the boundaries of existence are sometimes defined not by what we observe, but by what we dare to imagine. In the quiet corridors of early 20th century physics, a revolution was unfolding. one that would forever change the way humanity understood matter, energy, and the universe itself. Schrödinger's wave mechanics emerged not as a small refinement of existing theory, but as a profound reimagining of reality. It offered a new lens through which the invisible architecture of the atomic world could be observed, described, and understood. The elegance of the equations belied the depth of their implications, creating a bridge between abstract mathematics and tangible physical phenomena. At the heart of wave mechanics lies the concept of the wave function, a mathematical expression that captures the state of a system in its entirety. Unlike classical physics, which focused on the precise location and velocity of particles, wave mechanics embraces probability, continuity, and the subtle interplay of forces. Schrödinger's insight was that particles, such as electrons, behave not as isolated points but as wave-like distributions, their behavior governed by a coherent and continuous set of equations. In this framework, the universe is not a collection of discrete, predictable objects, but a dynamic tapestry of possibilities, each woven into the fabric of reality through mathematical law. The transformative power of wave mechanics quickly became evident. Where the Bohr model of the atom could only offer approximations, Schrödinger's equation provided exact solutions for simple systems, predicting energy levels and behaviors with remarkable accuracy. It allowed physicists to calculate electron distributions, understand the structure of atoms, and anticipate the outcomes of experiments that had once seemed puzzling or inexplicable. With each calculation, the wave function revealed patterns that were invisible to the naked eye, illuminating a world of order hidden within apparent chaos. Wave mechanics also redefined the relationship between theory and experiment. Schrödinger's equations were not mere abstractions, they produced results that could be tested and verified in the laboratory. Spectroscopic data, chemical bonding, and atomic interactions all aligned with predictions derived from the wave function. This marriage of elegant mathematics and empirical validation gave wave mechanics its power and credibility. It demonstrated that the universe, though probabilistic at its core, could be understood and predicted with unprecedented precision. The philosophical implications were equally profound. Wave mechanics challenged the classical notion of determinism, the idea that if one knew the state of a system at a given moment, one could predict its future with certainty. In the quantum realm, such certainty is impossible. Instead, Schrödinger's equations describe a spectrum of potentialities, revealing the probabilities of different outcomes rather than a single definitive path. This recognition forced scientists and philosophers alike to rethink the nature of reality, causality, and observation. The act of measurement itself became a central concept, highlighting the subtle interplay between observer and observed. Schrödinger's wave mechanics also catalyzed the development of entire new fields of physics and chemistry. Quantum chemistry, solid-state physics, and particle physics all rely fundamentally on the principles he articulated. By providing a coherent framework for understanding atomic and subatomic behavior, his equations enabled researchers to probe phenomena that were once beyond imagination: the formation of molecules, the properties of materials, and the mechanisms of chemical reactions. In essence, Schrödinger's work laid the foundation for modern technology, from semiconductors and lasers to MRI machines and quantum computers. Yet, despite its mathematical rigor, wave mechanics remains poetic in its vision. Schrödinger himself saw beauty in the equations, likening their harmony to a symphony, a reflection of nature's own elegance. The wave function is not merely a tool for calculation, it is a window into the unseen rhythms of existence, a language through which the universe communicates its underlying order. Each solution to the equation is a revelation, a glimpse into the patterns that govern matter, energy, and the delicate interplay between them. Moreover, wave mechanics transformed the role of the scientist. No longer merely observers of a predictable world, physicists became participants in a universe of probabilities. The equations demand imagination as well as precision, intuition as well as logic. Schrödinger's work illustrates that understanding reality requires not only measurement but creativity, a willingness to see the unseen and to conceptualize what cannot be touched. The human mind itself becomes a part of the equation, navigating a landscape where certainty is rare, but understanding is possible. The impact of wave mechanics extends far beyond physics and chemistry. It reshaped philosophy, inspiring new ways of thinking about knowledge, perception, and the nature of existence. By revealing the fundamental uncertainty and interconnectedness of the quantum world, Schrödinger's equations encourage humility and curiosity. They suggest that reality is more than a series of discrete facts. It is a continuum of relationships, probabilities, and interactions, many of which lie beyond immediate observation. In this sense, wave mechanics is not only a scientific achievement, but a framework for contemplating the deeper mysteries of existence itself. In classrooms and laboratories around the world, Schrödinger's wave equations continue to guide inquiry and inspire innovation. From predicting atomic behavior to developing advanced technologies, the principles of wave mechanics shape the modern understanding of nature. Every electron cloud, every molecular orbital, every quantum simulation is a living testament to the power of his insight. By uniting mathematics, imagination, and empirical observation, Schrödinger created a tool that allows humanity to explore the invisible architecture of the universe with precision and wonder. Ultimately, the legacy of Schrödinger's wave mechanics is not limited to formulas or experiments. It is a testament to the transformative power of curiosity, the courage to question established truths, and the vision to see beyond the apparent world. His work reminds us that reality is not always as it seems, that the universe is infinitely more complex and beautiful than classical intuition suggests, and that the act of discovery is itself an ongoing dialogue between human imagination and the cosmos. Through wave mechanics, Schrödinger gave the world a new way to perceive, understand, and engage with the fabric of existence, a legacy that continues to unfold, challenging and inspiring generations to explore the mysteries of reality with both rigor and reverence. Erwin Schrödinger was not merely a physicist who solved equations, he was a thinker who probed the deepest questions of reality, perception, and knowledge. His work transcended the laboratory, reaching into philosophy and reshaping humanity's understanding of the universe. While wave mechanics and the cat paradox captured scientific attention, Schrödinger's broader influence lies in the way he challenged assumptions about certainty, observation, and the very nature of existence. He forced both scientists and philosophers to confront a fundamental question: how do we know what is real, and what does it mean to observe it? At the heart of Schrödinger's philosophical impact is the concept of uncertainty. Classical physics had provided comfort, a universe governed by deterministic laws, predictable and observable. Every cause had an effect, every motion could be traced. Schrödinger, through his wave mechanics, revealed that at a fundamental level, this certainty dissolves. The quantum world is probabilistic, and observation itself shapes reality. For the first time, human understanding could not claim to mirror reality completely. Knowledge became participatory, the act of inquiry influences the outcome, and the observer is intertwined with the observed. This insight reshaped philosophical thinking about the limits of science, perception, and even consciousness. Schrödinger's reflections extended beyond equations. He explored the tension between objective reality and subjective experience. The wave function, the cat paradox, and superposition were not just mathematical tools. They were metaphors for a universe in which certainty is provisional and knowledge is contextual. In his writings, Schrödinger questioned the nature of life, consciousness, and the human mind, suggesting that understanding the physical world is inseparable from understanding our own place within it. In this way, his work bridged science and philosophy, showing that the boundaries between disciplines are often artificial, and that the pursuit of truth requires both empirical rigor and imaginative thought. One of Schrödinger's most enduring philosophical contributions is the notion that reality is not a fixed entity, but a spectrum of possibilities. The classical view of an objective world existing independently of observation is replaced by a vision of existence as relational, interconnected, and dynamic. Particles are not isolated points, they are defined through their interactions, their probabilities, and their relations to other parts of the system. Life, in this view, is not a series of static events but a continuous unfolding of potentialities, where the observer participates in the shaping of outcomes. Schrödinger's philosophy urges humility. It reminds humanity that certainty is rare, and understanding requires an openness to ambiguity. The thought experiment of the cat became a cultural and philosophical emblem of this challenge. It is a metaphor for uncertainty, duality, and the interplay between knowledge and existence. The cat is both alive and dead until observed, just as reality itself is not fixed until engaged with. This paradox captured the imagination of philosophers, artists, and thinkers, illustrating that science is not merely about calculation, but about grappling with the nature of understanding. Schrödinger's work demonstrates that the act of knowing is inseparable from the act of being, and that the universe, at its core, is participatory rather than passive. Schrödinger also influenced the way scientific inquiry is conducted. By emphasizing the probabilistic nature of quantum phenomena, he encouraged scientists to accept uncertainty as an intrinsic part of the universe. Predictions are not absolute, experiments explore likelihoods and correlations. This approach shifted scientific methodology, fostering creativity alongside analytical precision. Researchers learned to embrace ambiguity, to model possibilities, and to understand that even incomplete knowledge can lead to profound insights. In doing so, Schrödinger's philosophy reshaped not only physics but the very approach to scientific discovery. Moreover, Schrödinger's influence extends to human self-understanding. He challenged the assumption that consciousness is merely a byproduct of matter. Instead, he suggested that the mind and the universe are deeply interconnected, with observation and awareness playing a role in shaping reality. This idea resonates with later interpretations of quantum mechanics and philosophical discussions about mind, perception, and existence. Schrödinger encouraged reflection on how humans perceive reality, how knowledge is constructed, and how understanding is both a scientific and philosophical endeavor. His work also inspired interdisciplinary exploration. Philosophers, cognitive scientists, and even artists drew from his insights to reconsider the nature of perception, reality, and creativity. The wave function became more than a mathematical tool. It became a symbol for the interconnectedness of all things, a reminder that boundaries between disciplines, between observer and observed, are porous. Schrödinger's thinking invites us to see the universe not as a series of separate objects, but as an integrated whole where patterns, probabilities, and consciousness intersect. Ultimately, Schrödinger's influence on the philosophy of science is a call to humility and imagination. It reminds us that the universe cannot be reduced to certainties alone, that reality is more complex and mysterious than classical thinking allows. Science is not a static endeavor, it is an evolving conversation between human curiosity and the enigmatic universe. Schrödinger demonstrated that equations and experiments are tools not only for prediction but for understanding, and that the deepest insights often emerge when logic and intuition meet. His legacy endures in both thought and practice. Wave mechanics continues to guide research in physics, chemistry, and technology. The cat paradox challenges students and scholars to reconsider assumptions about reality and observation, and the philosophical implications of his work continue to inspire reflection on consciousness, perception, and the nature of existence itself. Schrödinger showed that science is not simply a description of what is, but a journey into what could be, a continuous dialogue between knowledge, possibility, and imagination. In this light, Schrödinger emerges not only as a revolutionary physicist, but as a thinker who reshaped human understanding. He bridged the gap between mathematics and meaning, between observation and interpretation. His work reminds us that to explore the universe is also to explore ourselves, that understanding the fundamental structure of reality requires both rigor and creativity, and that the boundaries of knowledge are always horizons to be expanded. Through his life and thought, Schrödinger leaves a legacy that is scientific, philosophical, and profoundly human, a testament to the power of imagination to illuminate the mysteries of existence. Erwin Schrödinger's work did not end with the equations he crafted or the paradoxes he imagined. It continues to reverberate through the corridors of science and human thought, shaping the trajectory of discovery long after his time. His wave mechanics provided a framework that transformed the understanding of atoms and molecules, while his philosophical inquiries challenged the very way humanity conceives reality. Today, Schrödinger's influence is seen not only in laboratories and textbooks, but in the ongoing exploration of quantum frontiers that he helped define. His legacy is a bridge between imagination and experiment, between theory and the ever-unfolding mysteries of the universe. In the decades following Schrödinger's discoveries, quantum mechanics became the cornerstone of modern physics, providing tools to understand phenomena that classical physics could not explain. From semiconductors to lasers, from atomic clocks to quantum computers, the practical applications of his work permeate every aspect of contemporary technology. Yet, the true measure of his legacy lies not merely in utility, but in the way he reshaped our conceptual landscape. Schrödinger taught the scientific community to embrace uncertainty, to accept that reality is probabilistic and relational, and to understand that observation and knowledge are inherently intertwined. His influence is particularly evident in the ongoing pursuit of quantum information and computing. Modern physicists manipulate quantum states in ways Schrödinger could only imagine, creating superpositions and entanglements that echo the principles he first articulated. The cat, once a thought experiment, has become a symbol for qubits that exist in multiple states simultaneously, demonstrating the enduring relevance of his ideas. Each experiment in quantum computing, each advance in teleportation of information, reflects the same logic of superposition, probability, and interconnectedness that Schrödinger envisioned nearly a century ago. Beyond the laboratory, Schrödinger's work continues to inspire philosophical reflection. By revealing the limitations of classical determinism, he encouraged a reconsideration of human understanding itself. His insights suggest that knowledge is not an external mirror of reality, but a participatory process shaped by interaction and observation. In this sense, Schrödinger's legacy is both scientific and intellectual. It challenges humanity to accept uncertainty, to see the universe as a dynamic interplay of possibilities, and to recognize that consciousness itself may be a participant in the unfolding of reality. The enduring fascination with Schrödinger's thought experiments and wave mechanics also underscores their cultural significance. The image of the cat simultaneously alive and dead has become a metaphor for ambiguity, duality, and paradox, concepts that resonate far beyond physics. Philosophers, artists, writers, and educators use this symbol to explore the nature of reality, decision-making, and perception. It serves as a bridge between the technical precision of science and the intuitive, imaginative understanding of life, demonstrating that Schrödinger's ideas operate on multiple levels simultaneously. In academia, his contributions continue to shape curricula, guiding students not only in the mechanics of quantum systems, but in the principles of critical thinking and conceptual exploration. Schrödinger demonstrated that scientific progress is not only about solving equations, but about asking profound questions, challenging assumptions, and embracing the complexity of the natural world. His work serves as a model for integrating mathematics, philosophy, and imagination into a coherent pursuit of understanding. Moreover, Schrödinger's influence extends into the realms of theoretical physics and cosmology. Concepts of wave functions, superposition, and entanglement inform contemporary research into the nature of reality at the smallest and largest scales, from the behavior of subatomic particles to the fabric of spacetime itself. His vision continues to inspire inquiries into the foundations of physics, suggesting that the universe may operate on principles far more subtle and interconnected than previously imagined. In this way, Schrödinger's legacy is not static, it evolves as science itself evolves, always challenging the next generation to question, explore, and innovate. Perhaps most profoundly, Schrödinger's work embodies the enduring dialogue between human imagination and the natural world. He demonstrated that creativity is not separate from scientific reasoning, that insight arises from the marriage of rigorous thought and imaginative speculation. By turning abstract mathematical concepts into concrete models of reality, he showed that the act of discovery is not merely analytical but deeply human, a testament to curiosity, intuition, and the courage to venture into the unknown. Even today, as quantum technologies advance at an unprecedented pace, Schrödinger's influence remains a guiding force. Researchers continue to test, refine, and extend his theories, exploring quantum entanglement, coherence, and the boundaries between classical and quantum realms. Each breakthrough is a continuation of his vision, an exploration of reality's hidden layers, informed by mathematics, curiosity, and an openness to mystery. In this sense, Schrödinger's legacy is both historical and forward-looking, a reminder that the quest for understanding is never complete, and that every discovery opens new doors to wonder. His life and work also underscore the importance of integrating philosophy into scientific inquiry. Schrödinger did not separate mathematics from meaning, he did not view observation as a mere mechanical process. Instead, he saw the human mind as an active participant in the universe, capable of conceptualizing what cannot be seen and engaging with the probabilities that define existence. This perspective continues to influence discussions in the philosophy of science, consciousness studies, and even artificial intelligence, demonstrating that Schrödinger's ideas have relevance far beyond traditional physics. Ultimately, Schrödinger's enduring legacy lies in the combination of insight, imagination, and courage. He challenged established truths, embraced paradox, and dared to envision a universe more complex and beautiful than conventional wisdom allowed. By doing so, he not only transformed physics but expanded the scope of human understanding, showing that science is as much about asking profound questions as it is about providing answers. His work remains a beacon, guiding scientists, philosophers, and thinkers toward new frontiers, reminding them that the universe is not merely a collection of facts but a living, dynamic interplay of possibilities waiting to be explored. In every quantum experiment, in every thought experiment, and in every contemplation of reality's mysteries, Schrödinger's influence persists. He exemplifies the power of imagination in scientific discovery and the necessity of questioning the assumptions that bind conventional thought. Through his equations, paradoxes, and philosophical reflections, he leaves humanity not with final answers, but with a profound invitation to continue exploring, to embrace uncertainty, and to participate in the unfolding drama of existence. Schrödinger's legacy is eternal, residing not only in the equations on a page, but in the ever-expanding horizon of human knowledge and curiosity, a reminder that the journey of understanding is infinite, and that the boundaries of possibility are limited only by the scope of imagination itself.